Justin Miller, Oxnard College Physics here, doing a little more oscillation here. So yeah, let's do another problem, shall we? Yes, we shall. This time investigating some phase constants, kind of looking a little bit deeper at that to see how we figure out what phase constants are and what they really correlate with. So here's the problem. All right, so we've got ourselves a mass spring system, and we're told that the mass attached to this spring is equal to 1.25 kilograms. Great. We're told that the amplitude of the oscillations is 15 centimeters, so we'll just call that 0.15 meters. And we're also told that the total energy of the system is 0.75 joules. So we have E total is equal to 0.75 joules. So this is what we've got to go with. The first question is, hey, what's the spring constant of the system? What is K equal to? So how are we going to get K? Can't use the mass. Can't use just the amplitude. Maybe the energy can tell us something. And oh my gosh, it can. That's right. We got that the total energy of the mass spring system is dictated by the expression 1/2 Ka squared. Great. That's it. The total energy is the sum of the kinetic and potential energy, and we derive this out. So with this, we've got that K is equal to 2E total divided by A squared, which is going to be equal to 1.50 joules divided by 0.15 meters quantity squared. We got ourselves some newtons per meter. Yes, indeed. 1.5 divided by 1.15 squared. 66.667. 66.667 newtons per meter. There's the spring constant of the spring. Great. Well, we could have just asked, what's the period of the oscillations? But in a sense, we need what K is first. Let's just go ahead and ask, hey, what's the period of these oscillations? Period is equal to a what? Well, the period, once again, is equal to 2 pi times the square root of K over M, where K is equal to this, which we just determined, and we can just go ahead and figure that out. So let's just say this is going to be equal to 2 pi times the square root of that divided by 1.25. And we get ourselves, 2 pi divided by, so 2 pi times the square root of M over K, not K over M. Get what M's are. Anyways, square root 2 pi times square root of M divided by 667. And we get that it's about 0.86036 seconds. All right, so great. What does that have to do with the phase constant of the system? Nothing. So let's go on and answer the next question, which specifically says, now, if at t equals 0, the mass is at the position x is equal to 5 centimeters, and is traveling downward, what's the phase constant of the system? And again, the phase constant correlates with the initial state of the system at t equals 0. So we're told, part C, at t is equal to 0, x is equal to 0.05 meters, and v is equal to, well, we don't know what v is, but we do know that it's going down. So v has to be negative, going downward. So utilizing those two pieces of information, one can discern what the phase constant is. How is that? Well, we know that x of t is equal to a times the cosine of omega t plus phi, right? Great. Well, now we evaluate this at t equals 0. We say, well, x of t is equal to 0, we're told must be equal to 5 centimeters above the equilibrium position, so it's plus 5. So we've got that that's 0.05 meters, and x of t is equal to 0 is equal to this evaluated at t equals 0, which is then equal to a times the cosine of phi. Great. Well, x of t equals 0 is equal to this, and must be equal to this. Thus, those two must be equal to each other. And we've got then that 0.05 meters must be equal to 0.15 meters times the cosine of phi. And that we can go ahead and solve for phi here. So we can get that phi is equal to our cosine of 0.05 divided by 0.15. Phis in radians. Our calculator's got to be in radians then. So what do we get out of it? Calculator's in radians, yes. And we've got the arc cosine of 0.05 divided by 0.15 is 1.23096. 1.23096 radians. All right, is that the answer? And the answer to that is maybe. Maybe. Why wouldn't it be? It's a good question. We'll answer that here in a moment. How do we know if this is the answer? We check it. We've got to make sure that we get the right direction of the velocity, because the object could be going up or down at x is equal to 0.05 meters, right? How do we know? Well, if we check it against the velocity. So now, check v of t is equal to 0. Must be negative. What is v of t? Well, v of t is equal to negative a omega times the sine of omega t plus phi. General expression for this velocity as a function of time, and v of t equals 0 is negative a omega times the sine of phi. All right. Well, a and omega, those are constants, and they are both positive. So really, when we're looking at this, we're saying that this all must be negative from this right here. So that means that the sine of phi better be positive, because positive times negative gives us negative, right? So the sine of phi must be positive, so that our v of t equals 0 is equal to negative. So we check it. We've got the sine of 1.23096 radians is equal to, we don't even need to know the value, we just need to know, is it positive or is it negative? And it turns out to be positive. So that means that this is indeed the correct answer. And you may say, well, how could it not be the correct answer? And we already alluded to it a little bit, but what if it wasn't the correct answer? How do we get the correct answer then? So let's change something. Let's go ahead and say that actually, part D, our initial position is going to be 0.05 meters at t equals 0, but instead of going down initially, it's going to be going up. That's when we start our stopwatch, boom, at t equals 0. So D, now let x be equal to 0.05 meters at t is equal to 0, and B at t equals 0 is positive. going up, or going in the positive x direction. So there we go. What do we change with this? Well, all that we've done is change the direction. How does that have any impact on this? Well, let's see, right? So we do the same sort of thing. We've got x of t is equal to, x of t is equal to 0. Must still be equal to 0.05 meters. We're still above the equilibrium position. And x of t is equal to 0, is equal to a times the cosine of omega t plus phi evaluated at t equals 0, which just gives us a times the cosine of phi. And well, we know what a is, 0.15, and what do we get out of this? We've got ourselves that phi is equal to the arc cosine of 0.05 divided by 0.15. You stick that in your calculator, and what do you get? You get this answer right there, 1.23096. Huh, how could there be another answer? Well, we started to think about the cosine function itself. It repeats every 2 pi radians. That's true, but there's symmetry with it. Symmetry in terms of, say, the x-axis, if we're looking at this versus this. So really, there's 2 values at which the cosine of this will give us phi, or I should say that the cosine of phi will give us this ratio. So let's go back to this. Cosine of phi is equal to, well, 0.05 divided by 0.15, right? So one possible phi is the 1.23096 radians. Is there another one? Cosine symmetric about the x-axis. It's an even function, right? Even function. If you have something that is in the first quadrant or in the fourth quadrant, you get the same result. That's it. The cosine of negative phi is equal to the cosine of phi. Even function. Cosine of phi is equal to the cosine of negative phi. That's the other answer right there. Boom, negative phi gives us the same thing. So when we go through this and solve this out for phi, really, there's a plus or minus there. There's 2 possibilities that solve that out. So phi could be equal to plus or minus 1.23096 radians. We've already found that positive puts us with the velocity going downward. Hopefully negative puts us with the velocity going upward. Let's check. Let's check. V is equal to positive at t is equal to 0 for phi is equal to negative 1.23096 radians. Let's check this out. So we've got, again, V of t is equal to 0, must be equal to a positive value going up, and it is equal to negative a omega times the sine of phi. Well, if this is going to be positive, the sine of phi better be equal to a negative value, right? The sine of phi must be negative. So we check it. The sine of negative 1.23096 is equal to, drum roll, sine of negative 1.23096 is negative, yay! And you know what? It's the same number as the sine of its positive counterpart, except it's negative. So what does that mean? Well, that means the object's going upward. That's what we wanted. So the correct answer is phi is equal to negative 1.23096 radians. So the point with this is that you got to be careful. You got to make sure that you're taking into account the direction that the object's moving at t equals 0 as well. Because there's two possibilities. It could be going up, it could be going down. And there's a particular phase constant that gives you the right one. So you need to know its initial position at t equals 0 and the direction that it's moving at t equals 0. And that's it. You can figure out what the phase constants are from there. Phase out constantly.